We have all relied on Ctrl+Z to rescue us from a typo or an accidental deletion. It feels instantaneous, almost like magic. But beneath the surface, your text editor is performing a precise, calculated trick. It tracks every letter you type, every format change you apply, and every deletion you make. Crucially, it logs this history as a sequence of events. When you press undo, the application does not just guess what to revert. It rolls back your timeline in the exact reverse order of how it occurred. The last action you took is always the very first one undone. This flawless memory relies entirely on a foundational concept in computer science. To understand how your computer manages this timeline, we have to look at the specific data structure running behind the scenes. This structure is called a stack. In the world of programming, a stack is a collection of elements that follows one strict, uncompromising rule: last in, first out, commonly abbreviated as LIFO. The easiest way to visualize this is to picture a physical stack of heavy plates in a cafeteria. When a clean plate is added, it is placed right on top of the pile. When someone needs a plate, they take the one from the very top. The plates at the bottom remain completely inaccessible until every single plate above them has been removed. You cannot pull a plate from the middle without risking a total collapse. In software, a stack works identical to this physical constraint. You can only interact with the item that currently sits at the very peak of the structure. To interact with this structure, programs use two fundamental operations: push and pop. When we want to add a new piece of data to our stack, we perform a push operation. This slides the new element onto the top of the pile, and a tracker called the top pointer shifts upward to acknowledge the new peak. When we need to remove an item, we perform a pop operation. This retrieves the uppermost element and pulls it out of the container, causing the top pointer to drop down to the item immediately below it. There are no shortcuts here. You cannot push an item into the middle, and you cannot pop an item from the base. By enforcing these two simple actions, the stack guarantees that our history is always preserved in strict reverse chronological order. Implementing this behavior in actual code is remarkably straightforward, because most modern programming languages have stack mechanics built right into their basic arrays. Consider a standard empty array in JavaScript. To build our stack, we do not need complex algorithms or massive lines of logic. We simply use two native methods that match our conceptual rules. Calling array push appends an element to the end of the array, treating that final index as the top of our stack. Calling array pop automatically targets that exact same final index, removing it and returning its value to the program. This makes the stack incredibly lightweight and computationally efficient, as the computer never has to shift or re-index the rest of the data. The utility of a stack extends far beyond the bounds of a text editor's undo history. It is deeply embedded in the core architecture of nearly every programming language through a mechanism known as the call stack. When a program executes, functions often call other functions. For instance, function A might invoke function B, which then triggers function C. The computer handles this nesting by pushing each function's execution context onto the call stack. Function C sits on top and must finish its job and pop off the stack before function B can resume. Once function B finishes, it pops off as well, returning control back down to function A. Without the stack, software would completely lose track of where it is running and where it needs to return. The true power of the stack lies in its intentional limitations. In computer science, imposing strict constraints often yields the highest efficiency. By restricting access exclusively to the top element, the stack eliminates the need for complex searching, sorting, or memory reallocation. It achieves blazing speed and absolute predictability with just two actions: push and pop. Whether it is tracking your nested function calls at the hardware level or stepping backward through your recent typos via Ctrl+Z, this simple engine of last in, first out architecture serves as a fundamental pillar of modern software engineering.